Hello everyone, welcome back to Dragonfly Engineering. So this week we're continuing with the Stoker Steam engine piston rod. This is the Stoker Steam engine that Keith Rucker is restoring for the Nashville Steam organization. And so this week I've decided, after looking at the results of last week, where I did the run-out test out at the Tailstock. You know, this is the concentricity and the diameter, or the cylindricity measurement. I was actually out by about 0.02 of an inch, or plus or minus 1,000ths, and it wasn't quite good enough for what I was shooting for. Keith requested a 1,000th, or to have the shaft be within 1,000ths, and I translate that to total run out of 1,000. So I really have plus or minus 0.5 and I was about plus or minus 1,000ths out at the end. So to fix that, so I've decided to scrap the first piston rod that we worked on, and we're going to start with a new one. So now I'm going to use the piston rod as a practice part. And I'm going to pull out the follow rest, which I purchased for the lathe maybe 5 episodes ago, with anticipation of potentially using it on Keith's project. The follow rest that I bought was, I think, for a later version of the lathe than I had, so I actually have to machine out a clearance area for some sheet metal on the x-axis. So I'll show you quickly how I did that, and then we load the follow rest. And then we'll do a little bit of work with the tension and the accuracy of the bearing on the live center. I actually had to switch back to a live center where I could adjust the tension. Let's head over to the Haas CNC mill, and we will machine out a clearance area for the sheet metal on the x-axis of the lathe. So where the blue mark is, I need to machine away about 0.2 inches to be safe off of this cast iron structure, so that I don't crash into the sheet metal housing when I'm moving the x-axis back and forth. So it kind of sucks, but you know, the lathe is 7 years old, and I bought this like 2 months ago. So you know, sometimes you just got to fix things. We probably will need some coolant though. Let me reduce this coolant down. So this cast iron, so it's going to create a bunch of like powder basically, and I'm manually using the Haas TM1 mill to do this, and I'll cut my marker off there. There we touched, so I'll just do an origin. And I'm just basically turning the hand wheels like it's a manual mill. I could probably increase the spindle a bit. Okay, so we'll come down. I'm running in millimeters, so we'll say 4 millimeters. And then we'll just hack off some of this excess casting. So now I'm doing a jog lock on the Haas mill to basically just hog through. So this is the sheet metal edge that I was talking about that causes me a little bit of problem for clearance. We get our bolts. Where did I stick those bolts? I just want to make sure I'm good. Let me zoom you in on you can see how the original casting overlaps the sheet metal housing for the X stage, which covers the servo motor and the gear mechanism, or the lead screw mechanism. It overlapped it by maybe 0.30 of an inch. So by cutting out this clearance, a generous clearance, now when I move the X back and forth, that sheet metal clears, which is kind of nice. So there we go. Let's move on to setting up our follow rest. Okay, we're going to do some experimenting on getting a more perfect concentricity on this super hard shaft that we're turning. So we're going to engage the follow rest. Now the next question is, where do the bearings of the follow rest lay relative to the cutting tool? And that is something I've looked online, and I don't really know. So online, some people say so if this is our stock, then the bearing should basically ride on the stock after you cut. And then other people say that the follow rest should actually reference the uncut portion, or the bearing should be ahead of the cutting tool. I do have experience on a much weaker, smaller lathe where I had the bearings riding behind the tool, and mostly because I didn't have any choice in that. It was an Inco lathe that's in my garage. But what happened with that is with the support bearing being, about an inch behind the tip of the cutting tool, at the beginning of the cut, it was cutting straight, but then I started to develop a wave in the radius of the part, and the length of the wave was basically the distance from the cutting tool to the bearing itself when I was following the cut. And I think what was happening is, the stock would push up or flex up against the bearing of the follow rest, and then which meant that the cutting tool was cutting a slightly larger diameter. And then as you're cutting forward, that bigger diameter then references the bearing behind the cutting tool and pushes your stock forward, which cuts a smaller diameter. So then as you keep cutting, now that new smaller diameter hits the bearing as you're traveling, and that imparts more of a deflection in your stock, which means that you're starting to cut a larger diameter again, which is slightly bigger than the last wave. And as you go down your cut, basically you're increasing this wave magnitude the farther you go, and you wind up with basically kind of a axially wavy part or cylinder. The alternative is to set up your follow rest to reference the stock before you cut it, which would get rid of that resonant wave pattern that you can get, and I'll show a picture of that. I've got a sample of a long aluminum tube that I cut somewhere around here. So anyway, if we follow the beginning of the cut so that we don't actually get a feedback loop in our finished cut, then we're referencing like the rough stock. In our case, it's a hot rolled bar. So I'm not sure which is better, but what I'm going to try to do is essentially have the bearing be almost coincident with the cutting tip, maybe just 50 thousandths behind or about 2.5 to 3 millimeters behind. So one of the things I'm working on here to improve the shaft concentricity accuracy is to dial in our live center. So this live center has a spanner ring that basically compresses the bearings inside of here. And I've noticed that there's a little bit of play in the live center bearing at the moment. So if I go ahead and touch off on the side of this other live center that I have, which has the ability to adjust the bearing with this spanner nut at the top. So right now we're at 0, and I've already tightened it a little bit, but you can see how just by moving back and forth, we've got about plus or minus 1/10,000ths, or about 5 microns of play. On this packing ring, there's a couple of spanner locations, a couple of holes. I don't have a spanner wrench, but you can get this is a cutoff ejector pin, 1/16 hard steel, and you can kind of tap the packing ring down, or basically I'm rotating or seating the bearing a little better. And we're looking at our accuracy, and there it's basically moving about 1/10. Now this is all kind of subjective because I'm also flexing the tailstock a little bit, and I don't have a specific force I'm applying, but I'm also spinning the live center to make sure I'm not binding up on the bearings. But basically we want to get as tight on the bearings as possible to wring out any kind of slop in our final turned part without adding air from the bearing getting too hot and things like that. So I'm going to spin the bearing, and we've got a 1 micron run out, so that's about 1/2 And then if I push, I'm pushing and pulling, I don't know, maybe 5-6 pounds, and we're getting 2 or 3 microns or 1/10 play in this bearing. So I can continue to do this. Now the trade-off is as this bearing's going to spin faster and faster. Of course, my spanner hole is overlapping where the indicator is right now. But as you spin this bearing faster with a tighter bearing, you generate more heat, more growth on the spindle, and then when you cool off or when you stop spinning, then the spindle will retract and it'll pull the tip out of your center in your stock, which adds inaccuracy as well. So it's a lot of fiddly, almost black magic work to dial in or to squeeze out tenths on your setup. But
we'll try that out. There is a couple of oil holes, so I can unscrew these screw holes and then put some oil in the bearings for the back bearing and the front bearing. So let's see if that helps. And here's my foam block to protect everything when we load the bar stock in. Oh, actually, this is a close to live part, except that, yeah, it wound up being 2/1000 undersize, unfortunately, and out of round by about 1/1000. So gives us the opportunity to optimize our process for cutting a perfect part. What do I do with my chuck? Hold on. Okay, so I'll probably wind up doing the rest of the CNC operations on this piece as our test piece. And then when everything is completely dialed in, then we'll do the real part. We'll clamp the tailstock into place. And then we'll tighten down. So since I've pulled this shaft out of the chuck and then we put the shaft back in the chuck, it's no longer, as round a referenced coaxially as it was when it was originally turned. But we're going to do test cuts anyway to see how our follow rest does. So now when I turn, I should be able to not be able to stop the live center with my fingers. So that means we're engaged pretty good there. All right, so we don't need our safety foam anymore. Add here on the end, close to the tailstock. It was plus or minus 1/1000, and our target here is 1/1000 total run out, or at least that's my target. I reloaded this shaft so it's no longer concentric in the chuck or out here at the tailstock. And you can see we are, let's see, is this the 0? And this is still that micron dial indicator. Yeah, so we are out of round by 40 microns, or almost 2/1000 of an inch. So that's not good enough for me. So what we're going to do is experiment with following. So let me pull this indicator out. I switched this tool out to a 1/64 tip radius. Our tool tip, our cutting leading edge is right here. And the brass bearings for the follow rests are going to be slightly behind, but not like an inch behind like I was talking about before. So to set the follow rest, what I need to do is start a cut and then basically stop the cut and then cinch down these brass bearings onto the surface with oil and then continue the cut, which is an interrupted cut. So in that in itself may be a good argument for having the bearings follow the front. But as you saw, our shaft is already out of round, and typically if you need to use a follow rest, then you're going to start with some stock that is not perfectly round anyway. Since we're trying to squeeze out every micron, we're going to have to deal with the fact that we're going to have to start and stop on the new piece of stock. This is the scrap piece with the CNC profile in the end. So we're going to have to start the cut and then stop the cut so we can set our feet onto the area that's going to have a post operation, the CNC taper, and then continue to the cut all the way across to see if we can help support the end of the shaft so we don't get that plus or minus 15 micron run out. All right, so let's go ahead and set up for that. I got some nice feedback from the comments to tell me to increase the RPM, so I'm going to go with 700 RPM this time. I was told to try 800 to 1,000. But with this shaft being 122,000 PSI yield strength, which is basically twice as hard as an off-the-shelf shaft, I still have to reduce the RPM a bit. Otherwise, the tool will not survive going across the face. Okay, so we're running at 700 RPM. Okay, so we'll call that 0. The other feedback was I need deeper cuts, but again, tool life is an issue. Hopefully not splash the camera. Oh, I changed the coolant, by the way. And I'm just cutting enough of a surface here so that the follow rest can reference. Now, I've seen people talk about burning in your brass bearings on follow rests, which basically it sounds like you just sit there and let the stock spin and rub in a groove into your brass. Not sure if that's a good policy or not, but I'm going to give it a try. I'm not completely on the bearings, so I probably do need to cut some more. Don't want to rub in an actual step into our brass follow rest bearings. All right, so I'll make these slightly snug just so that we get a good seat on our brass. And then I will do spindle forward. So now we're basically just rubbing down a seat, a profile into our brass. You know, like probably a tenth or so. We'll let that run for a little bit. Probably hear it changing over time. Actually, we go back and forth. Maybe that helps too. Yeah, I can see a slight hint of brass coloration on the steel there. I'm going to go ahead and snug up these a little more. The leading edge of our brass follow rest, which is like a 1/2 inch face, is approximately 0.1 inches behind the leading edge of the cutting tool. So the likelihood of this flexing and causing a resonant wave in the surface is very low in my opinion. Oh, and in general disclaimer, I usually use this lathe for cutting mold cores, injection mold making operations. So I typically don't deal with very long shafts like this. So this is a little bit of an exploration for me as well as you. But I'm sure some of you know better than I do about this, which feel free to provide guidance and suggestions in the comments. All right, let's do one more seating of the bearings here. You can see the brass color actually develop. So let's go ahead and hit go. Better get the coolant. I guess the coolant should share the follow rest bearing as well as the leading edge of the cut. All right, let me get the indicator in here and we'll see what we got as far as concentricity run out. I think I can fix the surface finish with deeper cuts per the recommendations on the comments, which are appreciated, of course. I did a real brief polish on the shaft, and the shaft doesn't look that great as far as surface finish, so I probably would have to do a deeper cut, which is a little tricky because you got to set up the finish tool, do a test cut at a reasonable depth, and then measure everything, and then do that same general depth of cut for your finish pass, and hope that you hit your target right on the money. Otherwise, you got to spend a lot of time lapping the shaft down. All right, so let me spin this shaft, and this is not rehearsed, so hopefully we'll see better results. Ooh, look at that. We are all the way out at the end, and we are getting plus or minus 1/10. Now that's, let's say plus or minus 2/10, or plus or minus 5 microns. So yeah, that follow rest definitely helped. It essentially reinforced the live center and the tailstock. The live center has a little warmth on it too. So that's cool. We didn't get that before. I think some of that needle bounce is just the subpar finish. Okay, we're down here by the chuck, and you can see that we are minus about 17 or 18 microns. There's minus 20 microns. Anyway, we're 20 microns off down here. So if I get the calipers out, or better yet, the micrometer. I'm miking out the diameter at the tailstock off camera. But at least we fixed our out of round, but it seems like we've got a cone. We've imparted a cone shape now into our shaft. Let me confirm that with calipers. All right, I measured the diameter run out from the chuck down to the tailstock, or the cylindricity, I think. And we are basically 4 thousandths smaller out here, 481, than we are at the chuck, 485. So with adding this follow rest, my dialing in of the tailstock is no longer valid. and such that I need to adjust the position of the tailstock. Since our diameter is cut smaller on this end, some of that is due to the fact that I was pushing on it with this back bearing and the top bearing. We got to push the chuck of the tailstock away from the cutter by 0.02 or 50 microns in order to, with this new setup with the follow rest, to cut the same diameter on the back side as the chuck side. The last time we turned this shaft, I didn't have this follow rest installed. And the shaft, I think, was actually flexing the tailstock and the live center and maybe the lathe bed a little bit. And now with this episode, when we added the follow rest, I have to move the tailstock back to the original position. Now with this hex key back here on this, and I showed this on the last episode, you can slide your tailstock back and forth. So what we need to do, based on the dimensions and the test cut we just did, is I need to probably loosen the set screw on this cross slide. And we're going to use that dial indicator that's in the tool holder to effectively move our tailstock. It's a tight fit back here. All right, so I loosen that guy up. Oh, and we moved 30 microns just from me doing that. Let me make sure we're moving the right direction. So if I pull so we actually want to move to 50 on this end because I pulled the plunger towards me and we were getting farther away because we want the stock or the stock to move that way so we can cut a bigger diameter out here on the end. Okay, so what I'm going to do now is turn this set screw such that we can move our tailstock. I need like a longer hex key here. Okay, so I'm loosening that. So it looks like what I need to do is tighten the other side. Unfortunately, I can't see, so I'm going to have to bounce back and forth a few times. Oh, I just can't see it. Let's see what that did. Oh, okay. Well, it almost got us there. I'll do a little bit more of that. 55. Well, okay. I think that's I could probably tighten this screw now on the front to push back on the back set screw so we're in good tension on these screws. So now I'm tightening the front screw to tension up basically and get us back to 50 microns or 0.02 of an inch. Okay, we're a little less than that, but the screw tension felt reasonably good. What we can do now is maybe drag this guy along and see if our needle doesn't change. I guess it doesn't really count because the diameter's smaller, so we got to do another test cut now. But it is saying that we are further over, so if I bring the needle back to 0, so there should be a 0.02 gap here, which equals the radius of, or 0.04 diameter. Okay, let's do another cut and see what happens. But this time I'm going to do a deeper cut to see if we can get a better surface finish. I'm a little reluctant to do a 0.40 cut, but this stock is already kind of wasted, so what are you going to do? And I'll do 800 RPM. Maybe I'll do 3 inches per minute. Again, I'm a little concerned about prematurely killing the tip of this cutting tool because of the hard steel that we're cutting. But sometimes you just got to experiment and optimize your process. Yeah, the finish does look better. This is 800 RPM, 3 inches per minute, 40,000th depth of cut. And stop. And again, I'm going to just finger snug this and then lock down the follow rests. I got to make sure these knobs don't crash into the chuck on the other end. And maybe we'll see a little brass rubbing out onto the steel. Okay, so it's been about a minute. So I'm going to go ahead and tell it to go. And we'll see how we do. I could see a witness mark where we were sitting. And our chip is longer, but it seems like the finish is a little better. Another thing to be concerned about is a chip getting up in between the brass feet of the follow rest and the stock that you're turning. Yeah, actually with 800 RPM, 40,000 depth of cut, and 3 inches per minute on this nickel chrome moly steel, the finish does look good. Let's just hope the tool lasts. This position of the follow rest, since we're following our cut, is only valid for this particular run of the turning operation. So, and I don't want to drag the brass back across our finish, which actually looks really good, or relatively good, even though I can hear the record player sound. So I'm still going to have to diamond hone this to get the record player sound out, but it feels better. So I'm going to go ahead and back off our follow rest brass feet here, and then we can pull our tool back and then go back to the beginning and see how our new dimensions look. The surface finish looks pretty good. So thanks everyone for your comments and suggestions on feeds and speeds. The big question is, did the tip of the tool live? I discovered that basically I need to switch the tool out from roughing the rod to shape and then finishing. So there's actually, because if I try to do it all with one tool, then at the end, the tool kind of dies and pitters out halfway through the finish cut, and I start to get grooves, and the radius starts to change. Okay, we'll get into our clean cut. So this is real time. I'm not doing any editing tricks, other than I may lock the focus on the dial. We'll set our dial to 0, and then I'll manually turn the lathe. Wow. That is plus or minus 1 micron, or a total run out right now is less than 1/10, about half a tenth. So that's real nice. Yeah, follow rest actually do work sometimes. Let me get all this out of here. Okay, so we'll see how we're looking as we go down the shaft. Okay, so we're about middle of the run here, and we are minus 5 microns on radius with a run out of still about 1.5 microns, or half a tenth. And then we'll go down to the other end. So I haven't changed the knob since we were out here at the tailstock. So let me spin the chuck again. And we're still minus 5 microns with a run out of, looks like it's plus or minus 1.5 to 2 microns, which is weird because this is the chuck side. You know, I mean, the chuck bearing probably has a 2 micron run out in itself, or 1/10. Maybe that's what I'm reading here. It's hard to say. You see if you're, yeah, okay. And then let's see how our real-time run out measurement looks. So we're next to the chuck right now. So if I slowly move our carriage forward, I've got the follow rest, pulled back. We can see how we're looking all the way up and down the shaft. Yeah, and the surface finish with that 800 RPM and 3 inches per minute, 40,000 depth of cut looked nice, or looks nice. So you can see we're drifting up to plus 5 microns or 2/10 out here on the other end of the shaft with a cylindrical run out of, and we're starting to pick up a little bit right here. But we're still basically round within 1/10 of an inch or 2.5 microns. And this is starting into the area where we actually set the tools and everything. So actually here, yeah, our diameter is, our radius is about plus 7.5 to 8 microns with a wobble of 2 to 3 microns or 1/10 of an inch, or 1/10,000th of an inch. And then if I just wrap it back, some of the there is some play in the bearings of the X table itself. But yeah, this is the acid test for true cylindrical runout. We'll have to fudge in maybe 3 microns or so for the table itself moving, or basically the bearings surfaces of the X table, or actually the ways on the Z axis. But yeah, this is looking good. I don't think we can do much better than this. All right, and with that, I will finish up this process of CNC turning the features on the ends of this shafts later in this week or maybe next weekend. Again, sorry for the delay, but I got slammed with the one-man shop needs and the current situation in the world. Okay, I'll talk to you later. Thanks for watching, and I'll see you soon.